We call x the independent variable because any value in the domain can be assigned to x. We call y the dependent variable because that value depends on x. We often use letters to name functions such as f, g, and h. The symbol f parenthesis x close parenthesis means function of x. So function is the f, could be a g or an h as well. Parenthesis in this case means of. So f of x is a function of x. And since y depends on x, we say that y is a function of x. Or in math, symbol y equals f of x. So the way that we write an equation using f of x instead of y is called function notation. So if I had a line y equals 2x plus 3, I can write that in function notation because that is a function. It would be f of x equals 2x plus 3. So instead of y, we just put f of x to put this into function notation. Let's write these equations in function notation. Number 1, y equals negative 4x minus 2. So this is a negative sloping line, right? This is definitely going to be a function. So I can change y to f of x instead. Everything else stays the same. So f of x equals negative 4x minus 2. For number 2, y equals 6. That's a horizontal line, which is a function. So I can change y to f of x. Everything else stays the same. F of x equals 6. For number 3, x equals negative 1 is a vertical line, and that's not a function. So I actually cannot write this in function notation because it's not a function. If we were to use the equation f of x equals negative x plus 2 to find the values here, and then we're going to write the corresponding ordered pair. So f of 3 means we put 3 in for x. So negative 3 plus 2, and negative 3 plus 2 is negative 1. So the corresponding ordered pair, remember that's x comma y, so the ordered pair would be x, which is 3, and then y, which we found to be negative 1. So our ordered pairs, instead of being x, y, are going to be x f of x, because y is a function of x. For f of negative 4, we're going to put negative 4 in for x. Everything else stays the same. So actually, negative 4, that's positive 4, and 4 plus 2 is 6. So we input an x of negative 4, and we got an output of 6 for f of x, or y. Number 3 is interesting because they did not give me the x value. They gave me the y value, or the output here. So they're saying if you put some x in, you get 3 out. So they're asking me to find that x if 3 equals negative x plus 2. So I'm going to solve this equation for x by oppositing the 2 from both sides. Then I have negative x on the right side, and 3 minus 2 is 1. So then I just need to get rid of that negative sign in order to have just x on the right side. And that's going to be a negative 1 when I divide. So this tells me that the input, which I had to find here, is negative 1, when the output, which was given, is 3. For number 4, they again give me the output, or the y value. So I have to complete the equation. so that the output -5 equals -x plus 2. And then I need to solve for x here. So opposite 2 from both sides, and that's going to be -7 equals -x. Just need to get rid of that negative sign here by dividing it from both sides. So that's going to be a +7. So I found the input of +7 that gives me the output that was given of -5 to complete the ordered pair. Recall that the domain of a relation from a set of ordered pairs is just a list of all the x-coordinates from least to greatest without any repeats. Can we find the domain of an equation that's in function notation? Yes, we can. So when finding the domain of an equation, we actually look for what x cannot be. And we assume that x is all real numbers except for the exclusion that we found. So we want to find the domain of each function here. Our first example, a, g of x equals 5 over x minus 2. So one thing that we know is that you cannot divide by 0 because that will result in some undefined value. So I know that I cannot have 0 in the denominator. What about the numerator? That can be anything. The numerator has no exclusions, right? A polynomial is defined everywhere. It has no exclusions from its domain. But you cannot divide by 0. So I'm going to take that denominator and I'm going to say you can't be 0. Okay. And then solve for x. So I'm going to opposite that 2 from both sides. That'll be a +2. And so what I'm saying here is x can be any real number except for 2. And there's different ways that we can write that. I can write it as a set. I can say that this is the set of x such that x is a real number. And x is not equal to 2. Close that set. Or I can write this as an interval. So I'm going to say that x is all real numbers except for 2. So what that means is from -infinity to 2, not included, and pick back up again at 2 and go all the way to +infinity. So that's what this says in interval notation. I don't know exactly which way we're going to need to write this, so that's why I presented this to you in all 3 ways. You could probably just say in words that the domain is all real numbers except for 2. So any other real number is in the domain of this function, but not 2. B is a little bit, maybe even trickier because it just says h of x equals 7. So I do get people who say, oh, the domain is 7, right? Well, no, because the domain is the input, not the output. The domain is the x values. So what can I put in for x? There is no x, which means I can put anything that I want and I'll still get 7 out, right? So that shows us that the domain here is all real numbers. You can write that in words. You can say the set of x such that x is a real number. I'll just put for number. Or you could do an interval notation, which is everything from -infinity to +infinity, right? All of these say the same thing. The domain is all real numbers. So we can also find the domain and the range of a function from the graph. And the domain is going to be all of your x values from least to greatest, right? And the range is going to be all of your y values from least to greatest. So this is left to right for x, domain. And this is bottom to top. for your y values, for the range. So let's find the domain and range of these functions that are graphed here and use interval notation. Okay. For a, this is what we have. From this point, negative 2, 1, continue to this point, 3, 2. So I'm just going to be looking at the x values, okay? So starting at the least x, that's negative 2, and it actually continues, you know, the points don't stop. They continue until 3. Do I include negative 2 and 3? Yes, because they are part of the domain. Those are defined endpoints. So that's going to be my domain, all my x values from least to greatest. But then I want to look at the range, which is all of the y values from least to greatest. So now let's look at y coordinates. So the lowest y is 1, and the highest y is 2. And everything between 1 and 2 is included because it continues. So those are included because those are defined endpoints. They're closed points, right? So those are included. Then look at example B here. I want my domain, so all the x values from least to greatest. So if I start on the left, that's actually an arrow. It's not an endpoint, it's an arrow. And what that tells me is this goes left forever. So that's going to be negative infinity. And then this continues to go right, and it doesn't stop going right. It keeps going right, and it keeps, oh, there's an arrow. So this is going to keep going right forever. So that means positive infinity. Do I include those? Those are not defined endpoints, right? Those are arrows, so I can't include those. Then the range is going to be all of the y values from least to greatest. So what is the lowest point on this graph? Right there at negative 3 for y. What is the highest point of this graph? Well, on this side you keep going up forever, and on this side you keep going up forever. Does that mean one infinity is larger than the other? No. So positive infinity is the largest y value. I will never get there. It's an arrow, so that's not included. But the negative 3 is a defined endpoint, and that is included.